Good day, students. Today, the topic of discussion is derivation of reflection coefficient and transmission coefficient of light when it falls upon an optically transparent surface. Okay, so on the picture shown here, you can see light, basically laser light, falling upon different surfaces. So on the right end, we can see light falling upon a mirror, a perfectly reflecting mirror. So this mirror completely reflects the light incident upon it. Okay, and hence we see reflection. Now on the second surface from the right, we see a glass plane. And when light falls upon this glass plane, light is observed to transmit through it. Okay, if you observe the edge, upper edge of that glass plane, you can see that the light is deviated a bit from its path, and that is due to refraction. When light falls normally upon it, the excitant ray will also be traveling along the same direction. Okay. So hence here we observe transmission of light through the glass plane. Now on the third surface from the right, we see light falling upon a white surface. Okay. So here the spot on the white surface is large. This is because white surfaces do not absorb any light at all. It completely reflects all the light falling upon it, and hence we see the spot due to the reflection from it. Now on the fourth surface from the right, that is the surface on the left end, we have a black surface, and the properties of a black surface is that it acts like a black body. So all black bodies absorb all radiations. Now hence when light is falling upon this black surface, we see that the spot is reduced. Okay, this is because the surface absorbs some of the incident light. Okay, hence absorption can be observed upon the black surface. So this picture has a lot of detail into it. Okay, now how do we measure the reflection from a surface? How do we measure the transmission from a surface? All of it depends upon a particular parameter of that surface, and let us find out that. Again, in this picture too, we can see a glass plane, and this glass plane shows the absorption of light, the reflection of light, and transmission of light. These are the three interactions that any optically transparent medium can have with light. The glass plane is seen to be a bit dark, a bit gray tinted because it is absorbing the light from the surrounding mediums. Okay, it is absorbing a fraction of light from the surrounding mediums. It is not completely absorbing it, but it is absorbing a fraction of it. Hence, it is observed to be dark tinted. Now, we can see the reflection of the bottle upon the glass plane. Hence, reflection is observed. Now, we can see the ball placed behind the glass plane. Hence, light is transmitted through the glass plane so as to make the ball visible. So, transmission is also observed. So, let us now quantify the amount of reflection and the amount of transmission. For that, let us define an electromagnetic wave. Let this be the direction of the z-axis, our optical axis, and a boundary be placed at z equal to 0. This boundary separates two medias of refractive indices mu1 and mu2. Now let us define the direction of the Cartesian coordinates. Our directions are defined by vectors, unit vectors I, j, and k. Here along this axis, let us have unit vector I towards the top and unit vector minus I towards the bottom. And along this axis shown, let us have unit vector k towards the right and unit vector minus k towards the left. Now in this dotted direction, that is towards the plane that you're looking into, let us have the unit vector j coming outward from this plane and minus j going inward into this plane. Now light is defined as an oscillating electric and magnetic field propagating in a direction perpendicular to both E and B. Okay, so the two parameters that I can define in a wave is its electric vector and magnetic vector. Let us assume incident light having electric vector EI and magnetic vector BI to be incident upon this boundary. So this is the light ray incident upon this boundary, the green ray, and these are the parameters of the unit vectors, unit vector I and unit vector j. Okay, let the electric vector be along the I direction and magnetic vector be along the j direction. Light falling upon the boundary will get reflected, and the components describing reflected light are electric vector ER and magnetic vector BR. This blue ray represents the reflected light, and the I vector represents its direction of electric vector ER, and minus J represents the direction of magnetic vector BR. Here you have to notice that the direction of the magnetic vector has reversed. The light transmitted through the boundary can be represented by the vectors ET and BT, electric vector ET and magnetic vector BT, that is transmitted through the boundary. The red line represents the transmitted light, and the electric vector ET is along I axis and magnetic vector BT is along the J axis. Since light is falling normally upon the boundary, perpendicularly upon the boundary, the transmitted light is also emerging perpendicular from the boundary. Hence, there is no change in I and J axes. The fraction of light that is reflected and the fraction of light that is transmitted has to be calculated. Now, to do that, we assume the general wave equation of light. It is given by electric field E is equal to the direction I into instantaneous value E naught into e raised to I kz minus omega t, where k is the propagation vector, z is the direction of propagation, omega is the angular frequency, and t is the time period of the wave. Similarly, magnetic vector B is equal to direction j into instantaneous value B naught into e raised to I kz minus omega t. Now, the green ray represents the incident ray. Hence, in terms of the E and B vectors, I can represent incident light as EI is equal to direction I into instantaneous value EI naught into e raised to I k1z minus omega t. Here, this I represents the direction axis, whereas this I represents the imaginary term. Okay. And k1 represents the propagation vector in the first medium. The refractive index of this medium has been renamed as n1. The wave is propagating in the positive z-axis, hence z is positive. And bi is given as direction j into instantaneous value bi naught into e raised to I k1z minus omega t. The fraction of light reflected from the boundary is represented by this blue ray, and it can be mathematically written as reflected light, the electric vector ER is equal to the direction of electric vector has not changed, hence I into ER naught into e raised to I minus k1z minus omega t. Here the negative term comes from minus z. The direction of this reflected wave has reversed. So z has become minus z. Thus this term is minus k1z minus omega t. Since it is in the same medium, the propagation vector is k1 itself. Now Br is equal to minus j, direction has reversed, into Br naught into e raised to I into minus k1z minus omega t. Okay, now the fraction that is transmitted through the boundary is represented by the red ray, and it can be mathematically written as transmitted light electric vector Et is equal to the direction of the electric vector is I itself. So I into Et naught into e raised to I k2z minus omega t. Here propagation vector is changed since light is entering into a medium of different refractive index n2. Thus we have the propagation vector k2. The direction of propagation is plus z itself, the positive direction of z itself. And the magnetic vector bt is equal to direction j into bt naught into e raised to I k2z minus omega t. I hope all of you are writing down the notes along with me. If not, you may pause the video and reach up to this point. Now, since the boundary is assumed to be at 0, z is equal to 0, this has been taken to simplify the mathematical forms. We can rewrite the vectors as incident light becomes EI is equal to I into EI naught e raised to minus I omega t, and BI is equal to J into BI naught e raised to minus I omega t. Here Z is equal to 0, hence K1Z terms vanish. The reflected light is represented as ER electric vector ER is equal to I into ER naught into e raised to minus I omega t, and magnetic vector BR is equal to minus J BR naught e raised to minus I omega t. In the transmitted light, the electric vector is represented as ET is equal to I into ET naught into e raised to minus I omega t, and BT is equal to J into BT naught into e raised to minus I omega t. Now, at every boundary, the Maxwell's conditions should be satisfied. Hence, for electric and magnetic fields at the boundary Z is equal to 0, Maxwell's conditions imply that the tangential components of electric and magnetic fields are continuous. Hence, at the boundary, the sum of electric fields on one side should be equal to the sum of electric fields on the other side. And in terms of magnetic field, we have the sum of the magnetic vectors on one side should be equal to the sum of the magnetic vectors on the other side. Hence, we get EI plus ER is equal to ET, and substituting this in terms of the wave equation, we get EI naught e raised to minus I omega t plus ER naught e raised to minus I omega t is equal to ET naught e raised to minus I omega t. Now we have the same term e raised to minus I omega t on both sides, right? So this will cancel, and hence we get EI naught plus ER naught is equal to ET naught. Let this be your first equation. Now the continuity equations in terms of magnetic vector can be written as Hi minus Hr is equal to Ht. Here, the minus sign comes because, yes, the magnetic vector of the reflected wave is reversed. Hence, we get this equation. Now, let us rewrite this expression in terms of B. We have the relation B is equal to relative permeability into H, mu into H. So, we get H is equal to B by mu. Rewriting it, we get Bi by mu I minus Br by mu. We get H is equal to D by mu. Hence, Bi by mu1 minus Dr by mu1 is equal to Dt by mu2. Remember, mu is the relative permeability of the mediums 1 and 2. Now, substituting for the general wave equations, we get Bi naught by mu1 e raised to minus I omega t minus Dr naught by mu1 e raised to minus I omega t is equal to Bt naught by mu2 e raised to minus I omega t. Now, cancelling the same terms on both sides of the equation, e raised to minus I omega t, we get Bi naught by mu1 minus Br naught by mu1 is equal to Bt naught by mu2. Let this be your second equation. Hence, Maxwell's boundary conditions of the electric vector and magnetic vector at z is equal to 0 is given by these two equations. Now, let us use a few more equations to substitute for B in these equations. We have used the first equation, B is equal to mu h, and the second equation we have the velocity of the medium to be the ratio of E by B. That means B is equal to E by V. Thus, the second equation can be rewritten as E I naught by mu1 V1 minus E R naught by mu1 V1 is equal to E T naught by mu2 V2. Now here we have this equation V is equal to 1 by square root of mu epsilon, where mu is the relative permeability of the medium and epsilon is the relative permittivity of the medium. Okay, so substituting that here, I can write square root of V1 is represented as square root of mu1 epsilon 1 into E I naught divided by mu1 minus square root of mu1 epsilon 1 E R naught divided by mu1 is equal to square root of mu2 epsilon 2 E T naught divided by mu2. That is square root of epsilon 1 by mu1 E I naught minus square root of epsilon 1 by mu1 E R naught is equal to square root of epsilon 2 by mu2 E T naught. Now, we have the relation refractive index of the medium N is equal to C by V. C is the velocity of light in vacuum, V is the velocity of light in the medium. Now, representing this expression in terms of mu and epsilon, I can write refractive index N is equal to square root of mu epsilon divided by square root of mu naught epsilon naught. Now, here we have assumed that mu is equal to mu naught. That is, the relative permeabilities of the mediums, of both the mediums, is the same. Hence, mu can be equal to mu1 is equal to mu2 is equal to mu naught. Thus, this expression becomes n is equal to square root of epsilon by epsilon naught. That implies that the refractive index is proportional to the square root of permittivity of the medium. Thus, taking these assumptions to this expression, I can write N1 EI naught minus N1 ER naught is equal to N2 ET naught. And let this be your third equation. Hence, from the first equation we had EI naught plus ER naught is equal to ET naught, and from the third equation we had N1 EI naught minus N1 ER naught is equal to N2 ET naught. This equation can be rewritten as N1 into EI naught minus ER naught is equal to N2 times ET naught. That is N1 by N2 into EI naught minus ER naught is equal to ET naught. Let this be your fourth equation. Now the fourth equation minus first equation implies your right hand side to be 0. Okay. And on the left hand side you have N1 by N2 EI naught minus N1 by N2 ER naught minus EI naught minus ER naught is equal to 0. That is N1 by N2 minus 1 into EI naught minus N1 by N2 plus 1 into ER naught is equal to 0. This implies that N1 minus N2 by N2 times EI naught is equal to N1 plus N2 by N2 into ER naught. We can write ER naught is equal to N1 minus N2 divided by N1 plus N2 times EI naught. Now, ER naught by EI naught is called the amplitude of reflection coefficient R, and that can be written as N1 minus N2 divided by N1 plus N2. Thus, the reflection coefficient or reflectivity capital R given by R square can be written as the whole square of N1 minus N2 by N1 plus N2 the whole square. Let this be your equation A. Now, using the first third and fourth equations, we are going to derive the transmission coefficient. For that, first, let us multiply the first equation with n1 by n2, and that implies n1 by n2 ei naught plus n1 by n2 er naught is equal to n1 by n2 et naught. Let this be your fifth equation. Now, adding the fourth equation and the fifth equation, we get 2 times n1 by n2 ei naught is equal to n1 by n2 et naught plus et naught. That is n1 by n2 plus 1 into et naught. We can rewrite this as et naught is equal to 2 times n1 by n2 into n2 divided by n1 plus n2. You can do the mathematics and get it like this into ei naught. Okay, that is et naught is equal to 2 times n1 divided by n1 plus n2 into ei naught. Now, et naught by ei naught is called the amplitude of transmission coefficient, represented by small t, and this is given as 2 times n1 by n1 plus n2. The transmission coefficient or transmittivity of the medium is given as the square of the amplitude of transmission coefficient, that is implied as 2n1 divided by n1 plus n2, the whole square. Let this be your equation B. Hence, we have derived the reflection coefficient as capital R is equal to n1 minus n2 divided by n1 plus n2, the whole square, and the transmission coefficient T as 2n1 divided by n1 plus n2, the whole square. Thus, when light is incident from a medium of refractive index n1 to another medium of refractive index n2, the fraction of light that is reflected can be obtained from reflection coefficient capital R, and the fraction of light that is transmitted can be obtained from transmission coefficient capital T. Also, by property of vectors, we have reflection coefficient plus transmission coefficient to be always equal to 1. With that, we have come to the end of today's discussion. Thank you.